Hi and welcome to this short lightning lecture about UrhoSharp and workbooks. And we want to talk about a very specific topic in UrhoSharp, and that's physics and collision detection. I'm René. I'm a senior content developer at Microsoft/Xamarin University. All the code that we see here today can be found in my GitHub repository. I'll have a link specifically for that workbook that we'll be seeing at the end of this presentation. So please stay with me here and check it out afterwards. What we're going to look at today is Xamarin Workbooks followed by UrhoSharp. So just quickly, what is Workbooks about? Workbooks is a way to quickly experiment with a platform. With Workbooks, you can create code, run it on the fly without going through this write code, build, fire up the emulator cycle. You can execute things pretty much immediately. And you can use Workbooks to target different platforms. Workbooks offer support for iOS, for Android, for Mac, for UWP projects. We have a lot of documentation at developer.xamarin.com. Just check out Xamarin Workbooks. It's a separate download. You have all the installation requirements over here, and then you're ready to create apps. The second thing that we'll look at today is UrhoSharp. UrhoSharp is the .NET or C# version of a 3D gaming engine. And this is a very powerful engine. You can find information at it, again, over at our developer website, developer.xamarin.com, Introduction to UrhoSharp. And it is a .NET binding to the original Urho 3D engine, which you can find over here at urho3d.github.io. So if you want to learn more about the internals, check that out. I'm not going to go into too much detail and rather want to focus on two specific topics on Urho that I personally found a bit difficult to figure out, and that's physics and how to handle events that are going on in UrhoSharp. So let's have a look at this. What you see here is the workbook environment. And in this workbook environment, we can select a profile that we're running in. So you can see I can create a console app here. I can create an iOS app. It's going to fire up the iOS simulator. I can run an Android app on the emulators. Here I have support for an app for the Mac, which is I'm currently on. And if I run the workbook app on Windows, you will have a chance to create a Windows application there. The idea of a workbook is that we have some descriptive text followed by some C# code. And I can really reference external components in there. So here I'm referencing the Urho DLL, which is what is giving me this 3D engine support. You can also add NuGet packages just by opening File, Add Package. You can import NuGet packages. And then you can use this as some sort of documentation or as a way of learning C#. So here we have some descriptive text, and then we have again a code snippet, and all of these code snippets can be executed individually. So we can explain that here we are importing the Urho DLL. We just click that and this has been executed. The Workbooks app will open a separate window in the case of a Mac application. Here it is. It's a regular window on Mac OS. And maybe I want to hide this browser here in the background to see this better. And that's where all the action will take place. So let's go through this and focus on the bits that I want to talk about today. We set up everything that we need for Urho first. So we import the namespaces that we need, and then we have to create a Urho application. And there is a simple application that we can use. It's an asynchronous one, which we simply await that. We initialize that with a specific window size, so that's the 1000 by 800 that you see here. We can set up some properties like touch emulation with the mouse, etc. And if we execute the workbook until here, that's what we get. So now, since I want to focus on physics and on collision detection, we also want to make sure to enable physics. And the physics world is completely separate of the visualization that we have in Urho. So we have maybe some shape like a sphere, and then we can assign a physical shape to that. So we can say this is a sphere with a weight of 1 ton, 5 kilograms, whatever. And then gravity will start to influence that sphere. To make that happen, we need to create the physics world component first. Moving on, we want to set up a scene. And every scene that we have has got a root node, which is by default somewhat off the center of the screen, so I'm adjusting that here. We need a camera to look at the scene. And what you see here is the scene. It just happens that there are no objects in it yet. So that's why everything is white. We need lights. Camera without light doesn't help. And again, we position that light somewhere in three-dimensional space. And then we want to get started with the actual objects. So the first thing that I want to add here is some sort of ground level. So what will my demo be about? Let's maybe quickly talk about that. I want to have a ground level, and I want to have some object above it, and I want that object to drop onto the ground level, bounce, and eventually fall off, following the physics. So step number one in here is to create that actual flow node. Let me see if I can find that here. Creating an element in Urho is done by creating nodes. So Urho is node based. You have parent nodes with child nodes, and then the nodes, they can have a component. And here in this case, the component that we have is an urho.shapes.plane. And a plane is not something that is flying. A plane is just, well, a rectangular area. So let's see what happens if we run our app up here. Now we can execute that, and here we get our plane. Next thing we need is something that will drop onto that plane. So that's the second object that I mentioned. And this will be a box in our case. So let me bring that up. We have our box node here. Similar steps, we first create a child, which will give us a node. The node has got a unique position in three-dimensional space. We can scale it. And then we say we want that node to be visualized as a box. We set the color. Here we say it should be red. We can also set a material. So you see I'm actually using a color as the material. A material can also be a texture. We'll see that later. I'll continue, and we have our box here. Because the physics world is separate from the visualized world, if you remember, our box is currently just sitting there. It's not doing anything. It's not influenced by physics. Before we add the physics, let's go ahead and adjust the position of the box a bit. That's our step number 3 here. I want to enter that here and copy that, move it a bit upwards, run this, and you can see we can change it. Feel free to play with this here. I can maybe place it a bit to the right, like that. And every time you execute this piece of code here, you immediately see a live update. So that's the power of workbooks here. So now the box is where we want it to be. And now let's talk about physics. In order to simulate physics, we need to add another component here to our box. We have to tell Urho what is this that we're dealing with here. It doesn't know that this is supposed to act like a cube that will fall down. So we got to give it that information. That's our step number 4 here. We will add a rigid body. And we do this for both, for our box and also for the floor plane. Because obviously we want the box to drop down onto that floor plane and make it bounce. So also the plane needs to have some physical properties. Now let's go through this. First, our flow node. Our flow node now gets a collision shape. That's what it needs in order to be able to detect collisions between those two elements. Next thing we set is here that our flow node is treated like a box. This is necessary because if we would create a physical object that is a plane, it would not have a border. So a plane would stretch out in every direction to eternity, but we want our box up here, our cube, we want to fall that over the edge here. So I say my floor here is also a very, very thin box. And we repeat this once more for our cube up here. So we see we create once more a rigid body. We give it a mass. In this case, it's 1. And if you compare this to the plane has a mass of 0. Because we want the plane to stay there. We don't want the plane to drop down if gravity acts upon it, but the box should drop. So that's why this box has got a mass of 1. We can set some restitution to influence how much it's going to bounce. We can scale it further if we want to. This is optional, has nothing to do with physics. Actually, I just want to make it a bit larger. And we once again set a collision shape. So now we have 2 collision shapes. And that means, well, those 2 will collide. And we can just run the simulation now. Let it drop. Now you see it's bouncing. And the nice thing is, if I repeat this, that there's a variation in there. So there's no guarantee that it will look the same every time. And if I do this often enough, well, eventually it will fall off. It will fall over the edge. So maybe if I place it somewhere else, I'm just going to put it a bit higher. So change the 8 here to a 10. Try that again. Now it's bouncing. And just a little more. And we see now it is falling. So there are 2 things that we might want to add in here. We see that the physics are apparently working. We have this collision that is going on. First thing is that we probably would like to be informed about the collisions that are going on here. Maybe we want to show some animation. We can do this. And the second thing is maybe we want to visualize the physical world. This is particularly useful if you're dealing with a situation where the physics doesn't quite work and you want to figure out what is going on. So first things first, detect the collision. That's what we do next in step number 5. There's a callback that we can use, and let me add that. So that's this one here. Here we use the subscribe to node collision method, where we can pass in a delegate that will be called whenever a collision is taking place. And we are interested in collisions of that box node, of our red cube that is falling down. If that collision between the box node and our floor plane here is happening, we can use the arguments that are passed in here, and we can figure out who or which object the box node collided with. It has got this other body property, and the other body is, well, in this case, our plane. We can get to the node, and if we have the node, well, then we can again change the node. And here I'm running an animation. So I want to visualize that the cube fell onto that floor plane by scaling the floor plane. You can see this here. I'm running an asynchronous action. Again, the beauty of C# here. I'm running an asynchronous action. I scale by 10%. Actually, I scale by 20% within 1/10 of a second, and then I scale back to 0.8. So let's just try this out. I'm going to restart the simulation here. Move that. You see it's falling. And we can see how the floor plane is changing now. Every time collision is taking place, it is changing. And have you noticed, by the way, that it's not falling down here? So we didn't change the original position, but there's some sort of randomization going on. You don't get the same results every time. So this is possible this is the way to subscribe to these collisions using these callbacks, and then in response you can influence the world. And the second thing is about visualizing the physics. This took me a while to figure out, so I thought I'm going to share that here with you. Here we are creating our physics world component, and it turns out we can add another component in here, and that other component is the debug renderer. If you just add the debug renderer, see what happens, you get exactly the same result. So having that component in there alone doesn't change anything. But we can use the debug renderer to output information about what is going on in the scene. And that's the next thing that I'm going to add in here, because we can subscribe to render updates. And let me think where I'm going to put this. So I'm probably just going to add a new code block in here. And into that code block, paste this part here. So we can subscribe to the engine's updates. Every post-render step, we can be informed. And in there, we can use that debug renderer to draw some debug geometry. And we can also let the physics component draw its debug geometry. And this part here will work because we have that component in there. So let's go ahead and actually, because we have this physics world component in there, sorry, because we have a physics world, we can call the physics world debug geometry renderer and use the debug renderer to visualize it. Now if I run this, we get some green outlines here around our objects, and now you can also see how my plane is really a box in the physics world. And also our red cube here, it has apparently the green outlines show me here that this is also treated as a cube. Again, the physics world is independent of what we're visualizing here. So what if I wanted my box, the red one here, to behave like a sphere? Well, I can do that. No one says that I have to create a rigid body that exactly matches what I see here. And this allows for some interesting effects. So here we are creating a collision shape, and we make that collision shape a box. So we could just change that. We say our collision node here, we want to set that as a sphere. Well, why not? And our sphere is going to have a diameter. Maybe we want to use a diameter of 2.0 f. It's got to have a position, so that would be vector 3.0. Want to center that, and we don't apply any rotation, so we just use the identity quaternion here. There we go. I'm going to restart this because it would not update the box node here because I check if the rigid body has already been generated. Let me run that again. Move that aside. And this sphere is maybe a bit too large here. There we go. Make it a bit smaller. Try 1F. But I think you have seen it. So here you see that inside my cube, I now have this sphere. And this green sphere, that's the result of the debug renderer. It's now treating the cube physically as a sphere. And apparently the physics simulation is a bit different here. It seems like it's always dropping exactly the same way, never rolling over the edge. I don't know if we change the height here even more. See if that influences it somehow. No. Doesn't change it. So you might want to use that in a game where you have some object and make it behave completely different from the way it's being visualized. So that's the two worlds that we have here, the visual world and we have the physics world. Now let's return that here, make it a box again, change it, and now we have the behavior again. And I want to remove the debug renderer now again because we see that everything is working as expected. I'm going to go up here and get rid of my debug renderer here. We also don't want to subscribe here to these events. And then everything's good again. So this is essentially it. That's what I wanted to share with you. How can we simulate physics? How can we detect collisions that are going on between physical objects? There's one last thing though, and that is currently our cube is falling over the edge, never to come back again. And we want to fix that still. So that's our step number 6 here. We have our, where is it? Gotta look for the right one here. This one here. in here. Here we can subscribe to the physics world PostStep event. So see here we have an event that allows us to subscribe to node collisions. And then we can also get informed about what is going on in the physics world. And that's why this debug visualization can come handy, because you want to understand what's going on. And on top of that, you can use this here. So here I'm getting an update whenever the physics world has performed one simulation step. And I can use that to find out if my box node is falling over this edge here. And what I'm doing here is, if that happens, I'm again using run actions async combined with await here, and I say I want to run an animation that moves my box all the way back up again to where it was. And then the whole animation is going to restart. So let me show you this. I'm going to retry here. Add this. It's falling. And I should probably update the height again. And you see it's falling down, and boo, it's moving up again. And it's repeating. And now you have a never-ending simulation of a cube dropping down on a floor node and animating back up. I want to fix this. Actually, we can leave it as it is. So why would we want to do such a simulation? Well, of course, it's always nice to have a demo, but we can actually use that to simulate some real-world problem. I presume you have a smartphone. And now you could use workbooks and UrhoSharp to simulate what will happen if you drop your smartphone. And to visualize that a bit better, we want to add some textures in here. So step number 7 is we get our floor plane, we assign some grass material in here. We have our box here. We change the shape of this box a bit. We change its scale and we texture it with some smartphone texture. Adjust the camera a bit, and then let's just run that and see what happens. If you drop a smartphone onto a grass surface, we can clearly see that nothing happens. The smartphone stays intact. So that's how you could use UrhoSharp. But what happens if we drop our smartphone? I want to adjust the height now. What happens if we drop our smartphone not onto a grass surface, but onto a stone surface? Well, we're just going to reset the animation, and boom, we see that would certainly be the end of our smartphone. And this is also the end of my little presentation here. Hopefully you enjoyed that. Here are still the links. Check out workbooks and UrhoSharp over at developer.xamarin.com. Grab the demo code for this short lightning lecture at my GitHub repository. And hopefully you have fun playing with UrhoSharp and workbooks. Thanks for watching.